Hello friends, good morning. Myself Dr. T. N. Oza, presenting to you a new video on a very important topic, postulates of quantum mechanics. I hope you will enjoy this and learn it by heart. The following postulates will be discussed. First postulate, second, third, fourth, fifth, sixth, and seventh. Here I must tell you, in some of the textbooks you find seven postulates, in some others you find six postulates. So there is nothing to worry about. All the matters will be covered. Introduction. As we know, quantum mechanics is approximate mathematical procedure for the determination of structure and reactivity of atoms and molecules. For this purpose, the formulation of quantum mechanics rests upon few postulates or axioms. These are a kind of accepted norms. Broadly speaking, there are seven postulates. A brief description of these postulates is given here. For the sake of convenience and brevity, we will take the case of a tiny particle of mass m moving along one direction, x direction, for example. However, analogous statements hold good for three-dimensional motion also. Now we discuss the first postulate, which is the beginning. Quantum mechanical state of any physical system being studied is represented by the state function, also called wave function, represented by a symbol, for example, psi xt. In place of psi, any other symbol can be taken, but psi is more popular. And this state function means that the function psi depends on the coordinate x and time t. So this is first postulate. Second postulate. Now we select a state function, then there must be certain properties of the state function. We cannot select any function as a state function. The function must fulfill certain features, certain characteristics. So regarding the characteristics of the chosen state function, it should be double differentiable and must fulfill certain other conditions. Firstly, the function psi xt, its first derivative d psi xt upon dx, and second derivative d2 psi xt upon dx2, they are continuous, not discontinuous. They are finite, not infinite, and single valued for all values of the x coordinate. Secondly, the function psi xt is normalized. That is, integration of the square of wave function psi square xt dx over the volume element dx between limits minus infinity to plus infinity must be equal to 1. In the formula, mathematical form, it is written here, integral limit minus infinity to plus infinity psi square x dx equal to 1. Also, equivalently, integral minus infinity plus infinity psi star xt multiplied by psi xt dx equal to 1. Sometimes the state function psi contains an imaginary quantity I, whose value is under root minus 1. Then complex conjugate of psi formed by replacing I with minus I is taken and it is multiplied by psi. Thus, instead of taking integral of psi square dx, we take integral of psi star multiplied by psi, then dx. This is why, just to eliminate I, because when you take the square of under root minus 1, it becomes minus 1. Next, we discuss third postulate. A physically observable quantity can be represented by Hermitian operator. An operator is said to be Hermitian if it satisfies the expression given below. Integral psi I star operator A psi j dx equal to integral psi j within bracket operator A psi I star. If this condition is fulfilled, then a physically observable quantity can be represented by a Hermitian operator. In this expression, the state functions psi I and psi j are meant to represent the physical state of the system. It is an atom or a molecule. Next, we discuss fourth postulate. The fourth postulate deals with the allowed values of an observable A. It states that the allowed values of the observable are the eigenvalues AI in the operator equation given below. Operator A psi I equal to AI psi I. Here you see the way state function psi I is on both sides, and AI is the eigenvalue. Capital A is the operator. And this kind of equation is called eigen equation. Fourth postulate. For example, in the eigen equation H psi E psi, H represents an operator, Hamiltonian operator. Psi represents the eigen function, and capital E represents the value of the observable physical quantity. Note that an equation is called eigen equation in which an operator acts on a wave function, for example psi I, yield the same wave function multiplied by a constant. Such equations are called eigen equations. Fifth postulate. The average value, or more appropriately the expectation value of the observable corresponding to the operator A, is given by expectation or average A of an observable. The equation is expectation value A equal to integral minus infinity to plus infinity psi star xt operator A psi xt dx. Sixth postulate. A very important postulate is about the construction of quantum mechanical operator. In quantum mechanics, normally we are involved in measuring physical quantities such as energy, position, and momentum. Corresponding to each observable, there exists a quantum mechanical operator. For example, for the classical variable position x, the quantum mechanical operator is constructed by writing x with a cap or using bold print. And the operation involves multiplication by x. Some more examples are given below. First column reads classical variable. Second column reads quantum mechanical operator. Third column reads operator. And fourth column tells what operation has to be done. Energy E. Operator is E. IH upon 2 pi L by dt means take first derivative with respect to t and multiply by IH upon 2 pi. Time t. It means multiplication by t. Momentum px means taking derivative with respect to x and multiplying by minus IH upon 2 pi. The square of momentum operator is minus h square upon 4 pi square d2 upon dx2. It means taking second derivative with respect to x and multiplying by minus h square upon 4 pi square I. Seventh postulate. The wave function psi xt evolves in time according to the time-dependent Schrodinger wave equation We can say that the wave function psi xt is the solution of the time-dependent Schrodinger equation, written as psi xt equal to ih upon 2 pi d psi xt upon dt. In this, h is the total energy operator, called Hamiltonian operator. Thus, h equal to t plus v, where t is kinetic energy operator, v is potential energy operator. The total wave function must be antisymmetric with respect to the interchange of all coordinates of one fermion with those of another. Electronic spin must be included in this set of coordinates. The Pauli exclusion principle is a direct result of this asymmetric principle. So, friends, we have enumerated all the 7 postulates of quantum mechanics. Each postulate must be understood because they are basic to the understanding of quantum mechanics. I hope 1 or 2 readings with a paper and pencil you can master these postulates. They are very easy to remember. I would advise you don't cram them, just remember them by learning their meaning. So, thank you very much.